Hello and welcome to QED Lecture 5 Part 9, the chi-squared test of association. Now, this one is used when we have two nominal variables. Now, if you think back to the previous tests, the t-test, the independent samples t-test, you have one numeric variable, which should usually be a scale variable, so a number, and you have one category. So the categorical variable, for example, the type of training that people have, the standard training or the rule of thumb training, that splits the population into two groups. And the other variable is the thing that you test to see if it's different or the same between the two groups, looking at the mean. The other kind of t-test we looked at was a correlation. That's when you have two numeric, particularly scale variables, and you're looking for a correlation between the scales. So you've got the t-test, which is looking for a nominal compared with a number, a scale variable. You've got the correlation test looking for two scale variables, but the one that's missing is nominal. That's when we come to the chi-squared test. So chi-squared looks for a correlation between two nominal variables. So you've got two categorical variables, x and y, and the terminology that's usually used for this is not so much correlation, it's association, because with correlation you're assuming there's some sort of order to it, but often the categories have got no order, they really are nominal. So it doesn't make sense really to talk about correlation. So we talk about association. So the null hypothesis is that variables are not associated in the population, and H1 is are associated in the population. Normally there's not a one-sided one. If you're dealing with ordinal data, so there's an order, then you could have a one-sided one, but then again the chi-squared might not be the best test for that. So most often chi-squared is just a one-sided one. So those are the two alternative hypotheses. And go straight to an example. So if you've got a rural area where, okay, they're growing various other things, but most of the staple crop fields, the main fields, are planted with maize, millet and rice. So gather data from a sample on the crops sown, and you also ask them, okay, is it a man or woman farmer working this field? And here's the answers. So just look at that. So is there any relationship between the sex of the farmer and the main crop they're going for in their fields? Okay. Well, does it look like it? I mean, there's more women growing maize, but possibly slightly more women farmers over on those. No, possibly not. Possibly more women growing maize proportionally. So part of the secret is to look proportionally rather than at the numbers, because there's slightly more men than women. So what we do is we say, the way this test works is it says, okay, what would you expect if there's no relationship? So if you have the same number of farmers, the same number of men and women farmers, and you also had the same amount of maize, millet and rice grown, the same distribution here, if there was no connection between the crop variable and the sex variable, what would you expect in here in these numbers? If it doesn't make any difference whether you're male or female, what crop you grow, what would we expect to see? I'll go through it step by step, so if this is too obvious or just too confusing, whiz through it. But the idea is that in this situation, 58 out of 115 people overall are growing maize. So if there's no relationship between crop and gender, then 58 out of 115, that fraction of women and that fraction of men should grow maize. So for the women, it should be 58 out of 115 of the women is 58 over 115 of 56. So that's the calculation you do. So you'd expect 28.24 women. So it's, well, okay, it's a fraction, but that's roughly what you'd expect, 28.24. Then you can do the same thing for the other categories here, and you expect this many men. So 58 out of 115 times 59 men should do it as well. By the way, this is not a minus sign, this is just an awkward bullet. So that many men should be growing maize as well. Then you can apply the same logic to the millet grower. So 31 out of 115 people grow millet. So should be 31 out of 115 times 56. 31 out of 115 times 59 should give you that. And then the same for rice. 26 out of 115. So that means that the proportions going this way are the same for women and men. You could also work it out going down the columns, the same thing. But let's just pause it one more thing. So as a shorthand, in all the cases here, if you're doing it by hand, the calculation is it's basically this number times this number. So this top one here is, well, let's look at the one here, the 26 over 115 times 56 is this times this divided by the total. And this last one is this times this divided by the total. So every entry in this cell works out as just the column total times the row total divided by the grand total. Gives you the answer for expected value. So once you've done that, you can compare what you actually got and what you'd expect to get if the null hypothesis is true. So if there's no connection between sex and crop choice, you'd expect this. What we actually got in our sample was this. As always with statistics tests, what you want to do is look at what you actually got and how far away what you got is from what you would have got if the null hypothesis is true. So you need a way of working out this distance here, measuring that. So what you do there is get the differences. So that's the differences. So you should be able to check that by hand. 32 minus 28.424 is this. So there's the differences. So the question is, how big are those differences? How surprising? So it looks like we got slightly more women than we'd expect growing maize, and slightly fewer men. Millet, pretty much bang on what you expect. Rice, fewer women growing rice, more men growing rice than you expect. The question is, how likely is it to get differences as big as that if the null hypothesis is true? And here we come to our friendly purple screen, which is the stuff we're not going to assess. You can show mathematically, but it does need some quite good A-level maths to show this, that. And basically, if you can understand the math, then you can understand what these subscripts mean. So Dij is that's the difference in the ith column in the jth row. That's the expected values. So that's the expected value in the ith column in the jth row. So what you do is basically this is saying you get all the differences that I showed you, square each difference, and divide by the expected value for that cell, and just add. This means just add the whole bunch up. So add all the squared differences divided by the expected value, add the whole bunch up. That gives you a number called chi-squared, so a capital Greek letter. That chi-squared distribution that chi-squared number follows a random distribution which we haven't met yet, which is called the chi-squared distribution. And by the way, it turns out it's just if you have normally distributed variables, if you square those and add them together, that gives you a chi-squared distribution. So that gives you a chi-squared distribution, and it's got two kinds of degrees of freedom. Yeah. So there are many different chi-squared distributions, and they differ by the degrees of freedom you have. But let's emphasize again, purple screen, don't think you're going to be assessed on that or expect us to know that in QED. It's just background for those that are interested. Maybe people that want to go on and do stats later to a higher level, then you will need to crunch into this stuff. But for QED, it's just for interest. Yeah, so that's just showing how you go through it. So getting each difference, squaring it, dividing by the expected value for the cell. That's the value you get for chi-squared overall. This is how many degrees of freedom you got. So it's number of columns -1, number of rows -1, 2 degrees of freedom. In Excel, you type in this formula here, which says, okay, hey guys, I've got a chi-squared value of 4.42. I've got 2 degrees of freedom. Tell me what's the chance of getting a number as big as that. In QED, of course, you just use data to do it. So here's what the data looks like. And this is where you need to tune back in, because this is what you do need to know. If you've got some data that looks like this, so there's not really any numbers, or if there are numbers, they're just representing categories. You've got two categorical variables. You want to know, is there any link between these? And we call that, as I say, an association. Is there a connection between the sex of the farmer and the crop that they're growing? Well, in Stacey, you do it like this. Output, basically use a tabulate command, which I didn't put in there, but you'll get it in the lab. Use a tabulate command to get out this. If you put the correct options in, it gives you the observed values, and it can give you the expected values as well. So we calculated above, and it tells you, here's the chi-squared, I should calculate it by hand. The key thing you're looking at for always is the p-value, so it's saying that if the null hypothesis is true, and sex and crop are not associated, the chance of getting differences as big as these is 0.1, it's about a 10% chance. From there on in, all the rest of it is exactly the same as any other test. There's the null alternative hypothesis, the p-value is this. Go back to this screen again, and here, doesn't even matter what kind of test it is. That's the p-value. What would you do in terms of those options? So please pause the video, think about this. Okay, so I hope you paused that. And the conclusion should be that because it's not less than 0.1, you can't reject here. If it was slightly less than 0.1, then you could reject, but it's not. It's bigger than even that. So you can't reject this, certainly not any of these. So you can't reject H0 at any of these significance levels. So the conclusion is you can't reject H0. So it's D. Yeah. So you can't reject H0 at the 5% significance level or even at the 10% significance level. So there's no particularly strong evidence here that men and women do tend to grow different crops. It's the conclusion for the policymakers. So it seems that there isn't any strong evidence. Okay, so that's all the tests that we'll consider in today's lecture, but we'll go on to something which is closely connected to tests, the idea of confidence intervals, in the next part of the video. But thank you for watching.